So trace formula, viewpoint, trace formula. So last time we talked about Poisson summation. Poisson summation. What does Poisson summation say? We did this in our favorite class F, but actually it's a much more general fact. So what does Poisson summation say? You have a nice function on the real numbers. Assume it's extendable. Assume it has moderate decay in x. Decay is like 1 over x squared. And it's extendable in some complex region, although that's because we're doing complex analysis. You don't need it to be extendable. Then what two things are the same?
The sum of the function values over the integers and the sum of the Fourier coefficients over the integers.
You sum, God, what is going on? I'm still getting used to this thing. You sum the function values over the integers, and that's a complex number. You sum the Fourier coefficients, the Fourier transform on the integers over the integers. These two things are the same. Okay, we saw a complex analytic proof. We saw the importance of this as a duality theorem. Let me show you how this is so proof 3, I guess. Proof 3 is that this is a baby trace formula.
Professor?
Yes?
Could we replace the integers with something else? Or like what kinds of things can we replace it with?
Well, that is exactly what the trace formula
Beautiful. Okay.
explains in general. So cool. That's exactly why I want to show you this. So let me be suggestive. I'm going to write G for my Lie group, by which I just mean the real numbers, and I'll write gamma for my discrete subgroup. Discrete subgroup of G, which for us is the integers, okay? So I'm just attaching fancy letters to objects that we already know and love, so that the next time, you see some lecture and someone's talking about the Langlands program, and here's the Arthur Selberg trace formula, and this is the baby version of what they mean. There are a lot of technicalities in what they mean that we will not see, but there are a lot of structural similarities to what they're talking about to what we will see, okay? And the point is to try to understand L2 of G mod gamma, which of course for us, so this is a nice Hilbert space. We have our Hilbert space, which is L2 of R mod Z. And there's a nice operator on here. So there's a Laplace operator, more generally a Casimir operator, but never mind. So this is our Laplacian. I'll just put the word Casimir operator, which for us is just two derivatives in x, right? And it acts on this space. And so this is a vector space. It's an infinite dimensional vector space, but never mind. We didn't do linear algebra the right way the first time we did it. We should have used infinite dimensional vector spaces and functional analysis, and then everything would have been clear. But too late now. We're going to do it. I guess when you get to, have any of you studied functional analysis? Is this something that, I don't know what order it comes in. Is it something that you take next semester? Do we not require functional analysis? We don't require it. Well, as you'll see, whatever you're doing, whether it's algebra or differential equations, you're going to be using functional analysis. There's right? All of mathematics is trivial until it uses linear algebra, and then it becomes deep. So whatever it is you're doing, you're going to need linear algebra. And this is kind of slightly grown up linear algebra. So we have a vector space, we have a linear operator, differentiation is nice and linear. So we want to know, can you diagonalize? We saw last time that this is a self-adjoint, right? We saw this last time. If I take the inner product, by which I mean the L2 integral of f and g, and I hit f with Laplacian, that's the same as moving Laplacian to the other side, which should be the adjoint, but it's its own adjoint. This is just differentiation by parts twice. And it decomposes this infinite dimensional vector space into an infinite sum, but a countable sum of eigenfunctions. So these are eigenfunctions of the Laplacian eigenfunctions of the Laplacian with eigenvalue. So these, of course, to be completely explicit, these are e to the 2 pi I mx. That's the function. And the eigenvalue, lambda m, so this is the spectrum of the Laplacian, is what? Does anyone remember? Or you could rederive it. You're taking two derivatives of the exponential function.
Negative 4 pi m squared.
Negative 4 pi m squared. Exactly. So the Laplacian is self-adjoint and it's definite. Negative definite.
Professor?
Yes.
Is that what Casimir means?
Casimir means it's generates the center of the universal enveloping algebra. Usually you have a Lie group and there's a Lie algebra, which acts by differential operators on the Lie group. And each one is just a first order operator. So the universal enveloping algebra is take all order operators in all Lie algebra there's sort of taking a derivative, directional derivative. So take all orders of directional derivatives, and there's an element that commutes, or there's a center of that algebra, this universal enveloping algebra. I'm just saying some words at you right now. And the Casimir elements generate the center. So that's kind of the picture that you'll see when you study these things. But for us, just take it to be the Laplacian. So there, in higher rank, there'll generally be more. There's not one Laplacian. Well, there is one Laplacian, but there are more Casimir operators. I mean, different people call these things different things. Okay, so we have this negative definite. We know what the eigenvalues are. So this is the spectrum, the set of these things. So this is like the spectral decomposition. So this is what we would call the spectral decomposition. Spectral decomposition of L2. So we have this Hilbert space, we have a differential operator. What's the spectrum of that operator? Now, this has some multiplicity, so it's not quite unique, right? It's an orthonormal basis, but I could have chosen the multiplicity of these eigenvalues because minus m has the same eigenvalue as plus m. So I could take some weird linear combination of em and e minus m for this eigenvalue space. In other words, when we diagonalize, so if you think of delta, if you go back to matrix world, back to matrices, matrix world, delta would be some matrix, I mean, an infinite dimensional matrix. And what we're saying is when you make this change of basis from whatever basis you had for L2 of R to this basis, so delta by change of basis, by change of basis to the EMs, we diagonalize. So how delta is similar to all of these eigenvalues, right? So there's 0, there's negative 4 pi squared when m is equal to 1, and when m is equal to negative 1. And then there's a negative pi squared times 4 when m is equal to 2 and negative 2, and so on. So we have these little lambda blocks. We have these 2 by 2 lambda. It's diagonal. We have two eigenvectors, but they come with multiplicity. And so as far as delta is concerned, it can't distinguish them, right? Any linear combination of EMs will also, of EM and E minus M will also give the same eigenvalue. Okay? All right. So, so here's what you're going to do. So what we want to discuss is constructing an automorphic kernel. So we want to construct an automorphic kernel. Kernel in the sense of like the Poisson kernel that you've seen in your homework, and even so here's a little aside, we can think of the Cauchy integral formula, Cauchy integral representation formula, right? We do 1 over 2 pi I integral over some circle, circle of f of z times the function 1 over z minus z0 dz, that comes out to, I mean, if z0 is inside the interior of the circle, you know what I mean. If z0 is inside a disk, and we're integrating over the boundary of the disk, what is the Cauchy integral equation, integral formula? Say that this comes out to? Yes, f of z0. Okay, everyone knows. Okay, this is an integral operator, and this is the kernel of that operator. So I can take any function. So we can call this an integral operator. Let's say I takes a function f and gives it a new function by doing this thing, by taking your f, integrating against another function. So this kernel is a function. This kernel, let's say k, is a function of two inputs. And what you do is you integrate out one of the inputs, and that gives you a new function. And Cauchy's integral representation formula says that this kernel acts like the identity. Okay, so that's another interpretation of the Cauchy integral representation formula. Does that make sense?
I have a quick question.
Please.
So is the kernel related to the kernel from typical algebra or algebra, where it's
so this is kernel in the sense of integral operator. Kernel is something that you integrate against, function in two variables, and you create an integral operator by integrating against the kernel.
So there isn't a connection between the two concepts.
You mean, why are both things called the same way?
Yeah.
In a sense, so something that, let's say, the kernel vanishes on will be something that f can't possibly see. So if this kernel operator, whatever it is, if it vanishes somewhere, and you're integrating a function that's supported outside of where the support of the kernel is, then that will also integrate to zero. So it's loosely related, but I don't have a good answer for that. I always think of these words as just being two different words with the loose connection, but maybe I'm wrong. Maybe there is a good reason why both things are called kernel. Yeah. Why are both things called kernel? There's like the two Spider-Men pointing at each other. They're both called kernel, but which one's which? Okay. Yeah. Right. So here's what we want to do. We want to construct an automorphic kernel. So a kernel, so this kernel, if you notice, it's really basically a function of z minus z0. I mean, it's a function that depends mostly on the difference, okay, up to an absolute value sign. I don't want to put an absolute value sign. So here's what we're going to do. We start with, so let's go back to Poisson summation, the beginnings of Poisson summation. We have our function f in this class, which is it's in some FA, and FA is things that are holomorphic on a strip with vertical part A. I'm just reminding you of this. We're never actually using any of this in the proof because this is a much more general concept. So we make a point pair invariant. We take what's called a point pair invariant, which is just a function k from, let's say, G to the complexes. G, remember, is just G cross G. So this is the reals cross the reals. So it's a function of X and Y. And what I will do is just stick it into F. Let's say like that. Okay? Or we can assume F is even. I don't like these, I don't love these absolute values So let's take them away. So let's say f is even. Just to simplify things, the point is that then what it means to be a point pair invariant is that if I apply the group, so if I apply, this is true even without this assumption. If I apply the group to K, so I translate by an element of the group, which in our case, the group is abelian and the action, our group is R, and the action is addition, and it's an abelian group. And so if G is a typical element of R, and I apply it to both places, what happens to this kernel?
It remains the same.
It remains the same. Good. Okay, so this is invariant under shifting. So that's important. So we have this thing. Usually you would write a group operation as multiplication, and maybe you want the action on the left or on the right, but here it's abelian, so I'll write it as addition. So usually you will see point pair invariants as things that satisfy something like this. Our operation in this case is addition. So let me not confuse you further by writing times when I mean plus. But when you see this in the real world, people are applying it to groups that act by multiplication, and they're not abelian. So you have to be a little bit more careful. But you want something, what it means to be a point pair invariant is that something that only depends, something that has this property. So this is the property of being a point pair invariant. It really only depends on the distance between x and y, because there's this isometry G that moves things around. And we accomplish that by taking the kernel to be a function of the difference x minus y. Then obviously if I shift both x and y by G, then that just cancels out and I get the original value. Does that make sense? Okay. Now this is not an automorphic kernel. This is a kernel on G. To be automorphic means on the quotient G mod gamma. So how do we we construct our automorphic kernel from our point pair invariant, automorphic kernel, one that's invariant, auto, same, morphic changes, so it remains the same when it's changed by an element of the discrete group. Automorphic kernel, big K. What should we do to little k to get something that is invariant under gamma, where gamma is Z?
Sum over elements of...
Exactly. Let's sum over elements. I'll call them n in gamma. This is kind of terrible notation. Usually you would write little gamma. So you would write little gamma in gamma, but I'll write n so that we're not too confused. Now, I can't do this. Why not?
That fixes it.
That fixes it. I'm just adding k of xy infinitely many times. Gamma is an infinite group. So that doesn't work. So how do I get it to be invariant? Well, let me try just doing this over one element. So then I get something that's definitely invariant. So if I replace x by x plus 1, then that's just changing which integer I put here. So this is definitely a function on R mod Z. What about in the y variable?
You can move the n to the other side.
Beautiful. This is also a sum over n in gamma of k of x y minus n, because I can move the n to the other side. And of course, the negative integers also run over the integers as n runs over the integers. So this is also a function that's invariant under R mod Z. So now we have created an automorphic kernel. So k, our automorphic kernel, is a function from G mod gamma cross G mod gamma to C. Now that we've created a kernel, what are we going to do with this kernel? What are kernels good for? Yeah, creating an integral operator. Exactly. Exactly what we said here, right? So we want to integrate against something. So kernel, so we make an integral operator, I sub k, but I'll forget the k. What does it do to some function g? So g is in L2 of R mod Z. So it takes automorphic functions, functions that are functions on the circle. And if I want to evaluate this at a point X, what do I do? How did it work before? We took this kernel of z0, integrated against f of z, and that gave us the value of the kernel at, well, this is at z0. This is at z0. We're integrating out z.
Do we take y to equal something and then let x vary? I should have flipped it, but something like that, right?
Yeah. So if I evaluate this is a new function. It's going to be a new function on the circle. If I evaluate it at x, what I do is I take g of y, I multiply it by my kernel k xy, and I integrate dy. This is on g mod gamma dy. Does that make sense? So I take gi and I average it against this automorphic kernel constructed from a point pair invariant. Okay, this is just for fun. This is not going to be on the test. So you can just relax and follow along and kind of enjoy this circle of ideas. So we have this automorphic kernel. This is kind of fun. What can we learn about this kernel? So the key idea of the trace formula is once you've done such a thing, you take its trace. Before we take the trace, well, let's just say what the trace will be. So a trace formula when I was an undergrad, I sat in, I guess I was a sophomore, and the juniors have these seminars where they read stuff and they present it to professors. So it happened that Andrew Wiles was running this, the junior seminar. So I sat in on it just to kind of see what it was like, sit in the back. And someone was giving, I won't say who, was giving a presentation on some Gauss representations and you compute the trace, yada, yada. And at the end of the talk, Wiles said something like, are there any questions? Of course, nobody had any questions. Everyone's too intimidated. And so Wiles had to ask a question. So he said, well, just humorous. How do you compute? You have this 2x2 matrix there. You say take its trace, but how do you compute the trace? How do you get the trace of a 2x2 matrix? And this was an undergraduate, so you have to forgive him. He thought for a minute and said, well, you compute the eigenvalues and then you add them up. I mean, yes,
Wonderful.
that is a way that will compute the trace. Is there an easier way?
Just add along the diagonal.
Just add along the diagonal, okay? So that's the trace formula. The trace formula is that the trace of a matrix on one hand is add the diagonal. On the other hand, it's add the eigenvalues. So this is the geometric side, because it's something about the diagonal, the geometry of what's going on. This is the geometric side. Geometric side. And this is the spectral side, because it's about the spectrum, the eigenvalues, spectral side. So there's something similar. There's something similar. We have a matrix. I mean, this IK is an integral operator, so it's some linear operator. So this IK is a linear operator. So it's some infinite dimensional matrix. Infinite dimensional matrix. You can think of it like that. And we want to take its trace and we want to compute the spectral side of the trace formula. So let's talk a little bit more about the spectral side. So we need the spectral decomposition of the kernel. We need to spectrally expand our automorphic kernel K of xy. So remember, what does K of xy, I mean, this is a function on R mod z cross R mod z. So let's take the spectral expansion in the y variable. In the y variable or in the x variable? Doesn't matter. I guess the way I've written it here, let's take it in the It doesn't matter. Let's take it in the y variable. So this as a function of y, so k for a given x as a function of y, this is in L2 of R mod z, right? Which we said before is decomposed by eigenvalues of the eigenfunctions of the Laplacian, which are these E sub m's. And so how could I recover the value of this? So for fixed x, how can I recover the value of this thing in terms of this basis in the y variable? Any
Do you
ideas?
use go for it.
Say it again, Ishan.
Do you replace G with E sub m?
I replace, so I want to project, I want to take this k, project it onto the E sub m's, and then multiply by E sub m's, right? I have an orthonormal basis, and if I add all of these up over the spectrum, so this is the spectral expansion of the automorphic kernel in the y variable. Does that make sense?
Is there a sense in which we're diagonalizing this? Because that's not clear.
That's exactly what the Laplacian has diagonalized. The Laplacian acting on L2 is diagonalized by this basis.
So we're not like diagonalizing the transformation I sub k. We're working with the diagonalized.
Well, what is this? What is this? It's the integral over R mod z, G mod gamma, k, x, y, and then, well, we have a Hermitian inner product, so it's sesquilinear, so I should put a conjugate here. So lo and behold, the projection is itself, the projection onto the EM isotypic component on this component of the Hilbert space is itself, well, up to this conjugation is the integral operator. Oops, the integral operator is the integral operator acting on EM bar of x, I guess. Does that make sense? Now, there's an amazing thing that happens when you have these integral operators and differential operators. They play very nicely together. So here's a basic observation. What happens if I take an integral operator on G? What are you calling this? A function of x, right? A function of x. And we differentiate twice in x. So I'm taking Laplacian of the integral operator. So I have one linear operator, and then I follow it up with another linear operator. So let's see if we can work this out. Well, by definition, this is two derivatives in x of the integral over R mod z, k, x, y, g of y, dy. Right? So far, so good. This is a nice space. There's no problem bringing this differential operator inside where it hits k. So this is equal to the integral over R mod z, two derivatives in x. That's the only place where x appears. K, x, y, g of y, dy. Now, what is a derivative with respect to x? It means you wiggle x a little bit and take a limit, right? Let's look at what dx, just let's look at one derivative. This is the limit of k of x plus something little over y minus k of xy over h, the limit as h goes to 0. Now we're just doing real variables, the simplest thing, right? But what do we know about this?
We could move the h to the other side.
We move the h to the other side. So we get k of x y minus h minus k of xy over h, and the limit. And let's turn this around. So this is x k of, I guess if I replace h by negative h, right? Limit as h goes to 0, I can replace h by negative h here. So I get a plus sign here and a minus sign there. Is that what I want? I claim this is also the derivative with respect to y. This is the same thing as differentiating with respect to y. So I move the h to the other side. It looks a little funny.
Shouldn't you have a minus sign?
Sorry?
I think you're trying to eventually show that dxx and I commute with each other, right?
Yes.
It's okay to get a minus sign on the first one.
That's true.
Right?
That's true. I seem to be getting a minus sign here. That's exactly right. Just like, remember when we showed that the Laplacian was self-adjoint? We moved it once, we got a minus sign. We moved it a second time, it remained, we recovered the plus sign. So the derivative here, yeah, very good. So if I replace h by minus h, I get x y plus h minus k xy over minus h. And of course, this goes to the derivative with respect to y of x k xy with the minus sign. And so when I do it twice, as I'm doing it here with the Laplacian, it's the same thing as two derivatives in y of kxy. Does that make sense? But the Laplacian is self-adjoint. So if I have an inner product, this is an inner product of, if I have an inner product of this k with this g, but I put a Laplacian in front of the k, so because delta is self-adjoint, that's the same as integrating over r mod z, k of xy, two derivatives in y of g. And so what has happened, this is the integral operator, not of g, but of delta g. What we've just shown is that the integral operator and the differential operator commute.
Professor?
Yes.
Earlier you mentioned that delta was a generator for the center of the linear transforms, right?
Yes.
Is it then the case that I was really particularly special? It was just commute with everything?
So it's that the differential operators, the Lie algebra generates differential operators that that will commute with integral operators. So this is a general fact. This is a general fact. The center of the universal enveloping algebra, this Laplacian or Casimir operators, will commute with integral operators generated by point pair invariants, even if you automorphize the point pair invariant.
But it's not more general than that.
It's not more general than that? What do you mean?
Well, I was just, is it that the center that we were talking about, everything else in the group are going to be
all
just
differential
these
operators? That's right. All the other differential operators commute with this one. We're not seeing anything here because we're just doing it on R. So you can't really appreciate, and I don't want to take the time to do this over a more general group, but we can't at the moment appreciate what those words even mean. But when you study later on, you'll see Lie groups and Lie algebras and how Lie algebras are directional derivatives on, locally. You have some tangent space to a point on a manifold. This is what Lie was originally thinking about, trying to make sense of all these things. And so you have this vector field of derivatives, and that generates an algebra of derivatives, because you can take higher order derivatives than just first order, right? Tangent space is linearizing everything. You can take higher order derivatives. And so that generates an algebra of all differential operators. And there's a center, and the center is generated by these Casimir operators, which in this case is just the Laplacian. I'm just saying words at you, but they're not things that will make sense until we actually look at the general picture, which we're not going to do this semester. I just want to plant some seeds, okay? So, so what is the consequence of the fact that these things commute? Suppose you have an eigenfunction. Suppose you take, you see, we're taking this inner product, we're taking the integral operator of an eigenfunction. So consequence if EM is an eigenfunction of the Laplacian, well, what happens? The integral operator of delta EM is just the eigenvalue of IEM, right? But this is also, hello, okay. But this is also delta of I of EM. So IEM is also an eigenfunction of delta with the same eigenvalue. So this integral operator, so IEM, is also an eigenfunction of the Laplacian with the same eigenvalue. But we know what the space of things that have that eigenvalue is. It's two-dimensional in this case. And in general, if you have some orthonormal basis, you're trying to figure out, maybe the spectrum is simple. And here we have multiplicity. So we can't quite say, then we know what IEM is. In this case, we can just compute. Everything is nice and simple here. So we can just compute. Let's compute this inner product. Okay, so we're trying to compute what these coefficients are. Let's compute Fourier coefficients. Compute Fourier coefficients of kx dot. So what I mean is, let's compute the inner product of kx dot with EM. So this is an integral over R mod z, big K of xy, E M y bar dy, right? Does this make sense? So what should we do? We have an integral over R mod z, and we have an automorphic kernel. Remember, this kernel was the sum over the integers, over the group of little k, x plus n, y. So what should we do when you see a sum? You have an integral over g mod gamma and a sum over gamma. Remember this unfolding idea? So we have to fix a fundamental domain. So we'll fix a domain, let's call it D, for R mod z. So now we can integrate over this domain, and we'll open up the definition, and we'll pull the sum out. So let's do it one step at a time, but in a second, I'm about to pull the sum out of little k of x plus n, y, g is E sub m of y bar dy. Okay, does that make sense? Okay, so we pull this sum out, and then what should we do inside? So we pull the sum out. We're integrating over this domain. The domain is like the interval 0, 1 or something. Take your favorite interval. We have k of x plus n y E m y bar dy. How could we simplify matters?
Because the picture of all of us is blocking the.
Oh, I'm sorry. You can see the picture of all of you?
Yeah.
Oh, I thought it wasn't showing that. Sorry. I keep trying to flip back and forth to see where you guys are. For some reason, I thought when I put things on top of this, it doesn't show that.
I think it depends if you're sharing your screen or just sharing this screen.
Oh,
I think that's the difference.
I see. Ah, God, I'm really screwing this up. All right, go on. So what can we do to simplify this? Well, it's the shift has happened at x here, but we're integrating over y. Why don't we move the sum, the n, to this side? So let's cut out the n and move it here as a minus n. And then let's make a change of variables. Y goes to y plus n. So that shifts d. Let's do this one step at a time. A sum on n in z. I can't believe I did that. K of x, y. So we've shifted this. E m y plus n bar dy remains the same. What happens to the range? Instead of integrating over 0, 1, we've done this before, right? We're integrating over n to n plus 1. But this thing was something invariant under gamma. It's e to the 2 pi I mn, n is an integer. I'm just reminding you of this unfolding process. This is unfolding again. We saw it last time. Right? Yes? Great. So this integrand no longer has any n's in it. That's what we saw before. The integrand no longer has any n's in it, so it's an integral of kxy e m y bar dy with over what range? So we've taken this interval 0, 1, we've translated it by all the elements of gamma. We've taken a fundamental domain for G mod gamma, R mod Z. We've translated by all the elements of gamma and summed over all the elements of gamma. So we just get the integral over all of G, which for us is R. Right? So it's again this unfolding idea. Great. So that's a very general process, a very general thing that happens all the time. But now we can really go into what K was. If you recall, K was defined. How did we define K? K of xy was f of x minus y, where f was that original seed function that we were studying. So look at this. We get an integral over R of f of x minus y. These are just real numbers. E to the minus 2 pi I my dy. So let's make a change of variables. Let's call this variable z. Well, we can just make a change of variables. Y goes to y plus x. Let's do it like this. Z is equal to x minus y. Okay, so z prime dz is equal to negative dy. X is fixed. And y is equal to z minus x. Thomas, something you don't like?
Sorry, this might be why did the plus n go away
This plus n.
when we did the unfolding? No, the one in EM.
The one
EM
in
of y
EM,
plus n.
because E is a function that's on G mod gamma. It's on R mod Z. So it's invariant under translation by integers.
Right, okay. Okay, makes sense.
If you like, it's e to the 2 pi I m y plus n, but this plus n is an integer multiple of e to the 2 pi I.
Okay, okay, cool. So in the general case,
In the general case, we still have a function that's on G mod gamma, and we're translating by gamma.
Right, okay.
So it's still invariant. That's the beauty. This is a function. That's the amazing thing about these functions. These eigenfunctions, or at least hypothetical eigenfunctions in general, are already automorphic themselves. So that's why this unfolding process is a very general process. And what you would take in general, if you were here and you have some spaces, you would take something like x inverse y. So that when G acts on both, G will move G inverse to the left and G to the right, and they'll cancel. In other words, an aside, generally you can take something like x is some function of x inverse y, which is basically what we're doing, right? The x inverse is, we've done y inverse x instead of x inverse y. X inverse is negative x. This is negative x plus y. The point is that then k of gx, gy is f of gx inverse, which is x inverse g inverse times gy.
So it seems like here the Casimir operator almost like induced our big gamma.
So we didn't use the Casimir operator here.
Or just like, because we diagonalized the Laplacian, and
yes,
that gave us Z essentially.
Well, this is true.
Sort of.
So this calculation has nothing to do with the fact that we have an eigenfunction of the Laplacian. All it has to do with is it's a function on G mod gamma. It's an automorphic function.
Okay. So this is just the sort of like comes from the decomposition of our G mod gamma. This EM.
This calculation is just unfolding. If you take the inner product of big K with any function that's automorphic, what you'll get is an integral over little k of that function over the whole group instead of over G mod gamma. That's just unfolding process. Where we're going to use that this is an eigenfunction is, well, we know a priori that this has to be some eigenfunction and it's with the same eigenvalue. So that actually means it has to be some multiple of EM itself, or E negative M, depending on which one comes out of the calculation. They both have the same eigenvalue. Thomas, does that make sense?
Sort of, but I'm still not sure how we got the, like, it seems like we have this like happenstance connection between the gamma that we're using and our diagonalization of the Laplacian.
Right. So
like, what if we had chosen like 3Z as our subgroup?
Yes.
You know?
Yes. Then the EMs would be different EMs. They'd be EM e to the 2 pi I over 3 M's.
And we'd want a different Laplacian as well, right?
Well, it turns out that the Laplacian comes from R, not from Z.
That's what I thought. So, I mean, if we had like root 2Z as our discrete subgroup.
Yes.
We wouldn't have that invariance in the EMs.
Well, so the EMs would be e to the 2 pi I over root 2 x. And when you translate that by an integer multiple of root 2, the root 2's on top and bottom still cancel.
Wait. Why would the EMs be over root 2 if they're coming from the Laplacian?
Because, so this is if gamma was root 2z, right?
Yeah.
So our EMs, EM of x, would be e to the 2 pi I m x over root 2.
So these would diagonalize the Laplacian?
Yes.
Professor.
Okay.
Because let's look at what the Laplacian is. Laplacian of EM is two derivatives of this thing times itself. So the eigenvalue would be negative 4 pi squared m over root 2 squared. All you've done is scaled where the eigenvalues are times EM itself. So there's still eigenfunctions of Laplacian.
I think one way we may be able to clear this up is to note that the Laplacian is actually a function from is acting on L2 of R mod Z,
Yes.
right?
Yes, exactly.
And then you could do for any like quotient, right?
That's right.
Does that make it clear, Thomas?
That's exactly what we're saying.
Yeah, that makes sense. That makes sense. Okay, so we're specifically looking for we're specifically diagonalizing it over G mod gamma. We're
Yes.
not diagonalizing it in general. Okay.
Yes, that's
got
right.
It.
The
Got
EMs.
it.
Okay, yeah, good. Good.
Thanks. Yeah, that makes sense. Thanks.
The EMs come from gamma. Gamma
Right.
determines what the EMs are. Otherwise, if you're doing L2R, that's a much bigger space. In general, that's I mean, we're doing L2R because we're doing Fourier analysis on the line, but we're understanding things about Fourier analysis on the line from the circle. I mean, that's where Poisson summation lives. It's this duality over the circle in the trace versus the geometric side versus the spectral side of the trace formula.
Professor, is it
Please.
true that if you diagonalize the Laplacian on G, that a subset of those eigenfunctions will then be when quotiented? Is that always true, that quotient idea?
So it's definitely true that when you have things that are on G mod gamma, well, they're also functions on G, just by forgetting the fact that they're invariant under gamma, and they'll be eigenfunctions.
Okay.
Of the Laplacian.
That's
what
clear.
they will not be is they won't be L2 of G.
Unfortunately, I see.
You see, if I have a function that's integrable on 0, 1, so this is R mod Z, so I have a nice L2 function like e to the 2 pi I mz, like a sine or something. This is beautifully an L2 of R mod Z. It is definitely not L2 of G, because I just continue this forever. I'm not decaying. So being L2 of G, but they are still eigenfunctions of Laplacian. Does that make sense? So when you restrict your domain, you're allowing for much more general, you're allowing for functions that wouldn't be an L2 of G to be an L2 of G mod gamma. But whatever they are, they're automatically eigenfunctions of the Laplacian because the Laplacian doesn't care about gamma. Does that make sense?
I think what confused me was the fact that it seems like these E sub m's are they form like a basis for L2 of R or something like that.
Oh, they don't. They definitely don't form a basis of L2 of R.
Oh, okay. So
Right.
for some space on R, right?
They form, right. So the EM,
I'm not sure which. I think that was the thing. I'm not sure which.
So over Z, they form a basis for L2 of R mod Z. What Fourier analysis that we've been doing on the line, the E sub X's, where Xi ranges in all of R, so this is continuous spectrum, as opposed to discrete spectrum. So this is discrete spectrum.
Ah, right. Okay. Yeah,
These
makes
functions
sense.
actually are individually in L2 themselves, whereas none of these are in L2. These are not in L2 of R. They have absolute value 1. You can't square integrate this. They're just barely not in L2. They're almost in L2, but they're not. But they do form a basis for L2 of R. That's the Fourier inversion formula. Right? The fact that they form a basis is the Fourier inversion formula. What are you doing when you do Fourier inversion? F of x is equal to the integral over the spectrum, and the spectrum is R, of the inner product of f with exc times exc bar. dc. Right? It's exactly the same idea, except now instead of a sum, you have an integral. So this is continuous spectrum. Continuous spectrum. Because the eigenvalues are still the same eigenvalues, right? The eigenvalues are still lambda c is negative, what is it, 4 pi squared c squared. But now this varies continuously.
It's kind of weird that they're a basis for a space they're not in.
Right. That's what continuous spectrum is. Continuous spectrum is kind of weird.
Isn't it like you do your Fourier, or you do it in short space and then extend by continuity?
You mean, how do you make sense of this in functional analysis?
Maybe.
There's a resolving kernel, which is identity minus s times delta, which you want to invert. So this is the resolvent kernel, which is yet another kernel, which is not immediately related to the previous two, at least. And this is a linear operator. And so I minus s lambda is a linear operator, and it either is invertible or it isn't. If it's invertible, then s is not in the spectrum. Where this has no inverse, I guess let me write it as delta minus si. Maybe that's a more obvious thing to do. Although, let's write it as delta minus si. Right? You take your matrix minus eigenvalue times the identity matrix, and you take the determinant of that and set it equal to 0, because that's where it's not invertible. That's how you find the eigenvalues, the spectrum. Where this thing has no inverse is where s is in the spectrum by definition. So now I'm really giving you kind of more general definition. So the spectrum of delta is the set of s in C with multiplicity. So it's not a set, it's a multiset, where this has no inverse. Where the resolvent has a pole. Okay, now I'm really taking you too far afield. I'm not supposed to be doing any of this. And I thought I'd take you a little bit afield, but now I'm taking you way too far afield. So can we finish the computation of what the nth Fourier coefficient of the kernel is, or the mth? So that's what we're studying here. We were starting to compute what the mth Fourier coefficient is. We know that whatever it is, I mean, this is the integral operator acting on em, or em bar. So it has to be some multiple of em bar, or e minus n. Bar, same thing. So we're almost there. Let's compute this. So far, so good? Yeah, let's finish this computation and then we'll take a little break. We're almost there. So we were up to the integral of f of x minus y, e to the minus 2 pi my dy. We were making a change of variable z instead of y. Z is x minus y, dz is negative y is, so this ranges now over the reals, but in the opposite order, but there's a minus sign here. So you get the reals again, dz, f of z, that was the whole point. And then e to the minus 2 pi I m y, which is z minus x. Since x has nothing to do with dz, so it just pulls out. What is this? Everybody see that? It's the mth Fourier coefficient on the real line of the original function f that we started with. You see that? So the integral operator of k acting on em bar is just a constant multiple of em, And that constant is the Fourier transform. The general version of this is called the Selberg-Harish-Chandra transform. So the general version, I'm just planting some more seeds in your name, in your brain. The names for these things are Selberg-Harish-Chandra, transform, which in this case is just a Fourier transform. In general, it's closely related to a Fourier transform. And we've expressed, so this k of x comma y, we've expanded in the y variable as a sum over the spectrum. This inner product is exactly what we just computed, f hat of m, e m of y times em of y. I want a bar somewhere. I should have gotten a bar somewhere. Sorry. EMX, that's good. EMX. Okay, this was the inner product. This was inner product of kx dot with em. So we integrated out the y variable. This is a function of x. What function of x is it? It's em of x times the Fourier transform. Okay, does this make sense? So now this is the spectral expansion of the automorphic kernel. Spectral expansion, because we're summing over the spectrum, parametrized by m, spectral expansion of our automorphic kernel, big K. Let's take a little break and let's say 5 minutes, and then we're almost there. We're almost up to the trace formula. Go. Okay. So so what have we done? We have this integral kernel, I, K. What does it do to a function g? It takes a function g and does this to it, k of xy, g of y, dy over r mod z. And this is now a function of x, so this is a function of x. We have given a spectral expansion of k. So the spectral expansion is that k of xy is a sum over m. We computed these Fourier coefficients, and we got them to be f hat m. I really want this to be a m bar somewhere. I dropped a bar somewhere. Let me just put it there. There should be a bar. Should be a bar. And let me leave that as a question mark. Maybe not. So here's what I want to do. So now let's take the trace. So take the trace of this integral operator. What does that mean? On one hand, it means you sum over the diagonal. The diagonal, instead of x and y, we have x and x. And by sum, I mean integral over the diagonal k xx dx. That's taking the diagonal of this operator and just adding it up. So this is the geometric side because it's the diagonal. This is the geometric side. And this will be equal to the spectral side, which we'll get to in a second. Let's mess with the geometric side for a minute. So what is the geometric side? Again, we have an integral over r mod z, k, big K, the automorphic kernel, which we can write as a sum over the integers of the little kernel, k of x plus n x dx. To write it like this, I have to pick a fixed fundamental domain. And then we unfold. Exactly as before. So I reverse orders. K of x plus n x, except now I can't easily get rid of this thing. right? But let's remember what k of x plus n is. It's f of x plus n minus x. Remember k, this is using how we constructed the point pair invariant was f of x minus y. So this is x minus y. So this is a sum over the group integral over d. I mean, these x's cancel. So we just get f of n times the length of d. The length of d is 1. Ah, that looks familiar. On the other hand, we're going to use the spectral expansion. On the other hand, this is also equal to, so now let's do the spectral side. K of xx is a sum over integers m of f hat of m em x bar em y. But y is equal to x. And I integrate this, so that's k of xx. This whole thing is k of xx, and I integrate this over d. So this is a sum over m in z, f hat of m. This is norm, this is why I wanted the conjugate there. This is norm em squared, which has f's of value 1. So I'm integrating 1 over d. So times 1. So this is the spectral side of the trace formula. This is the geometric side of the trace formula. And the two are equal, and that is why Poisson summation is a baby trace formula.
So what does the trace formula look like for some other group, say?
Right. So for compact quotients, if G mod gamma is compact, and you have a decomposition of L2 of G mod gamma, let's say, well, let me just use the same. We don't know what this looks like. We don't know what these eigenfunctions look like. Then it will say a function over gamma is a, well, I've written this as a sum, so let's write this as a sum over lambda m in the spectrum. In other words, which is the thing that we diagonalize this with respect to. And there's some transform, the Selberg-Harachander transform of the eigenvalues. So this is literally the geometric side and the spectral side. And that's why I insist on using the integers, which is the geometric group, and the spectrum. This is these n's and m's have completely different roles from this point of view. So this is what a general, the beginnings of a trace formula look like. Now, what you really want to do is you want to apply this when this is not compact. And then you have lots of technical problems that arise. And that's the beginnings of the Selberg trace formula. But that I really shouldn't talk about. Gosh, I really wanted to get to at least a little bit of stuff. We have Paley Wiener coming. I basically can't do anything. I have 1 minute left. I think that's okay. I think that's okay. We've maybe slowed things down sufficiently, and the next lecture can begin on Friday with back to complex analysis, back to our regularly scheduled program.